Hello and good morning from Germany again to our today's webinar, Efficient Quality Assurance on Insulating Materials as part of CE compliance. My name is Alexander Frenzel. I'm with NETZSCH since 2005 and I'm responsible for the business field management in the field of glass, ceramics and building materials. And today I would like to talk about quality control of thermal insulating materials as a part of the work you need to do to produce CE compliant insulating materials for the European market. Okay, what we can offer here at NETZSCH is equipment for checking, measuring the steady state thermal conductivity on thermal insulating materials. And what you see here on the left side, the three units in green and gray are our actual heat flow meters, our new heat flow meter line. And on the right side, you see our guarded hot plate. Let's start roughly a little bit with a technical overview. Our heat flow meters are able to run in a temperature plate range from -20 to 90 degrees C. And our guarded hot plate, the big one on the right side, is able to run in a temperature range from -160 degrees C up to 600 degrees C. Of course, that temperature range, as you see in the device, you need a kind of tight chamber and some cooling devices and more technical equipment to reach that high temperature level. But today we'd like to concentrate a little bit on the typical QA situation. So what I like to do, or what I like to reach as a QA engineer. I think it's quite simple. All of the people are want to insert a sample, press a button, and get a result. Of course, very easy, nothing to think about, and yeah, that's it. And of course, European manufacturers who are producing XPS, EPS, glass wool, polyiso, and all the other insulating materials want to get their product certified and want to survive third-party controls or volunteer quality controls, volunteer controls from external institutes, for example, to get a key mark certification, to get a RAL quality sign or something like that. And of course, everybody of us want to save money in daily quality control and want to have the data organized in an efficient way. This is a typical sticker, what you find normally on thermal insulating materials, which you can buy in a shop. And in Europe, it's all about in Germany, we say Nennwert der Wärmeleitfähigkeit, which is the declared thermal conductivity. It's all about the value which you see in the red circle. Where it comes from and how to measure it and how to determine it in an efficient way with all the documentation work which is necessary, we will talk about in this webinar. The determination of the nominal value of thermal conductivity is not a single measurement value. It is based on a statistical evaluation on a bunch of tons of measurements. Some of our customers in that field are measuring 700, 800 sample per year, where the statistical value is based on. If we look what that means, we see a Gauss curve, something like a Gauss curve. you see the mean value of your measurements, and you see in the right corner the so-called Lambda 9090 value, which is the mean value plus the standard deviation times a confidential factor. And what you get is the value for thermal conductivity, which is 2 on 90% of your production outcome with a probability of 90%. So you guarantee your final customer that the product which he uses in his building or in his application has, with a 90% similarity, this declared thermal conductivity. The recommended method for quality control of thermal insulating materials is the ISO A301. This is the standard for heat flow meters, how to build a heat flow meter. Where it comes from, if you look in your product standards, DEN 16162 up to 16172, so all the insulating material standards, those standards are relating to DEN 12667, 12664, and 12939. Those are the method standards how to measure thermal transmission properties on thermal insulation materials. And those are related to the ISO A301, which tells you how to build an instrument that can do this. And for the most users, this instrument is a kind of black box. So it's a kind of a pizza oven where you insert a sample and press a button and get your value out of it. And today I would like to bring some light into the dark. So let's start to talk about the principle of a steady state heat flow measurement. It's based on a formulation which comes from Jean-Baptiste Fourier. It's based on a temperature gradient between two sides of a material, temperature 1 and temperature 2. The temperature 1 and temperature 2 is different, so you get a heat flow Q through the material. And if you know the thickness of the material and the area where the heat flow goes through, you can calculate from the Fourier's law the thermal conductivity, which is called lambda, out of it. The principle of the measurement you see here, you see in the chamber a sample coming out. It lays on a bottom plate, and what you see is the top plate and the guard insulation around it. The plate on the top is the hot plate. The plate on the bottom is the cold plate. You can do it also vice versa. Between that, you insert the sample, which is in contact with heat flux transducers. And those heat flux transducers are able to measure the actual heat flow through the material. So, due to the fact that those heat flux transducers are in a certain temperature range and in a certain range of different heat flows, are not linear at all. A heat flow meter is a method which needs to be calibrated. It is calibrated by inserting a known sample, a so-called reference sample, and with this known reference sample with a known thermal conductivity, you can calculate, or the instrument itself calculates, a correction factor, which brings your measurement to a level which is traceable to an international recognized international reference material. The most common reference materials available on the market are the IRMM 440 and the NIST standard reference material 1450D. Both of them are mineral fiber boards. They have quite similar thermal conductivity. It's quite a little bit different. So we have 0.03 watt per meter Kelvin on the IRMM 440 at 10 degrees C, and the NIST SRM 1450D has a thermal conductivity which is a little bit higher. The uncertainty is given with lower than 1% or 1% at the 1450D. The bulk density is a little bit different. Important for the measurements in Europe, the IRMM 440, which comes from the JRC in Belgium, the Joint Research Center, sets the level for the European CE certification, and it is the reference material which is recommended in Europe. So some of you may have heard about a so-called transfer standard. There are also transfer standards available in the market, for example, from MPL. They offer EPS board as a transfer material in lateral dimensions of 300 times 300 millimeters and a thickness range from 25 to 50 millimeters. That comes from the reason that during a calibration, the calibration material should have similar thermal transport behavior like the sample you want to check later on. And this is the reason why sometimes it makes sense to make a calibration with a thicker material. Of course, I'm pretty sure you heard about the meaning of factory standards. Those are standards that we also deliver sometimes in combination with our instruments. On the left side, you see a borosilicate glass, which we use as a reference material for higher thermoconductivity. If you measure polymers, solid polymers, for example. And on the right side, these are our silica boards, which we sell, silica boards with which we sell with our guarded hot plate. Those are factory standards from our company, where you are able to check guarded hot plates, which are absolute methods to a higher temperature up to 600 degrees C. Okay, this is a calcium silicate board on the right side, as I said, for the higher temperature range. Important, the reference for calibration must be similar in its thermal transport behavior than your sample later on. How to figure out if my results that I get from the instrument after a proper calibration are good. And there is something that we can learn from the guarded hot plate field, which is a similar method, but an absolute method which there's no need for calibration. It's quite simple. So to check if a heat flow meter works in the range of thicknesses and the ranges of materials that you want to measure in your daily quality control, is you can run at first a linearity check. What is a linearity check? What you see here is the equation for the thermal resistance of a material, which is thickness divided by thermal conductivity. Our instrument gives as a result the thermal conductivity and the thermal resistance. And if you plot the thermal resistance over the thickness, and keeping in mind that R is thickness divided by lambda, which is a linear function, you should get a linear curve in that case. Of course, if the thickness, in this case, the thickness is extrapolated to 0, if the thickness of your sample is 0, the thermal resistance is 0. This is the reason why this linearity check should go to the origin, through the origin. On the right corner, you see the equation for a linear function. And if the thickness is 0, the resistance is 0, that means the y-axis offset t is 0. If you have a y-axis offset and t is not 0, this is dedicated to a part of contact resistance in your instrument. And the change of slope is a change in thermal conductivity. So that means from this linearity check, where you measure different thicknesses of the same material to check if your instrument is working linear for that material in that thickness range, lambda can be calculated from 1 divided by slope without the influence of contact resistance. And a proper measurement should deliver no contact resistance. That means T is 0. And you should have a deviation from this linearity in every point no more than 0.5% of the actual thermal resistance. We did this evaluation on our guarded hot plate on the Silcal boards, Silcal 1100, which are our factory reference standards for high temperatures. And to reach a proper thickness, we stacked those samples. So in the left graph, you see a measurement on 30 millimeters on 100 up to 600 degrees C. And you see on 60 millimeters, 2 stacked samples over each other, also in a temperature range from 100 to 600 degrees C. And what you see is that you have nearly zero intercept on the y-axis. So the contact resistances are negligible in that case. And of course, you have different slopes because the thermal conductivity is depending on temperature. On the right corner, right upper corner, you see an additional measurement where we stacked 3 samples on each other with the values for a 19 millimeter measurement. They are, of course, a little bit less accurate, but if you look at the zero offset, it is quite good, and that shows us that our guarded hot plate is also in a range of thicknesses where it's not made for a really, really reliable instrument, where we on our side can really check in an absolute way, in an absolute measurement, how the thermal resistance and the thermal conductivity of a thermal insulating material is. So that means you can send us also samples. We do also contract testing on materials, and based on those materials where we can deliver a factory certificate, of course, you can also calibrate with. So that means if you look on this linearity check in the region where the function or the measurement R versus D is linear, the calibration fits to your material. If you leave the linearity outside of these ranges, that could be a sign that you need to adapt the calibration, maybe with a thicker or a thinner material, or different thermal resistances, different materials. But this gives you a first nice impression about the accuracy of your machine. Okay, let's talk about the temperature niveau in Europe, which is connected with the quality control, the daily quality control in your factory production control, as an everyday control. The temperature niveau in Europe is, as you all know, 10 degrees C. And now it's all about physics. When we want to measure thermal conductivity in a heat flow meter at 10 degrees C, the setup is as follows. The upper plate is maintained on 20 degrees C. The lower plate is maintained on 0 degrees C. That you can reach a mean temperature of 10 degrees C. This is the normal standard situation for quality control in Europe. But there's a little bit of a problem. The corresponding standards for thermal insulation materials and for the heat flow meter procedure requests a difference between the lower plate and the actual dew point of 5 degrees C. When we look at the European standard temperature with a delta T of 20 Kelvin, you see in this calculation, when you have standard environmental situation of 23 degrees C and 50% humidity, the calculated dew point is 12 degrees C. So the lowest plus possible plate temperature will be 17 degrees C to overcome maybe problems with condensation on the plate, which with humidity in your sample and all that things. So this could be a real challenge to reach a proper environmental situation to fulfill this needs from the standard. And therefore, we have a couple of possible solutions. First of all, this is the thing that for example, all glass wool manufacturers are doing. Glass wool absorbs water if you have condensation in your measurement chamber. Glass wool absorbs water from the environment. So a lot of our customers in the glass wool field have a climate chamber, which is maintained to 10 degrees C and 10 to 15% humidity, which is quite dry. On the other hand, what we offer, you can connect a dry gas flushing to our instrument, which reduces the dew point in the cell to minus 30 degrees C, roughly. Yeah. So the workaround is to close the empty cell and purge it for a couple of let's say 20 minutes or something like that. And then you can lower the dew point inside of the chamber. You can insert a small measuring device to get a feeling for that, but you can lower it to up to minus 30 degrees C. That means if you flush it before you enter your sample, you close the door and you start your measurement. The risk of condensation inside of the instrument, inside your sample and on the plates is reduced to the maximum. So that means in that case, you have a chance for a direct QA measurement at 10 degrees C without influence of humidity. Or what you also can do, run a measurement on higher temperatures. In this plot, you see 3 measured points at 20 degrees C, 30 degrees C, and 40 degrees C. From this linear function of thermal conductivity over temperature, you can calculate the slope of the function, which is the so-called alpha lambda, the temperature coefficient of thermal conductivity. And by knowing this value, you can extrapolate from the straight line to a calculated lambda 10, which can be remeasured afterwards to get a feeling if there is a deviation and to get a feeling where the deviation comes from and to help you through that process and to overcome the challenge that you don't have a feeling which influence is coming from humidity and condensation. So back to the Lambda 1990 value. As I said, it is the mean value plus standard deviation times standard-based K factor, probability factor. Details on that you can read on my blog article, which is available at our blog website, TA Thermal Analysis, ta-netsch.com. Lambda 1990, simple explanation. You can search at Google and you will find it. So all the details about this value are in this article. And then let's come to what I call really efficient. I know it from many, many users in the field of thermal insulating materials that they do the documentation of their thermal conductivity values based on Excel tables. So that means every single measurement value needs to be entered in an Excel table. The Excel table calculates a Lambda 9090, and every 3 months or every 6 months, the notified body or the certifying institute is asking for the documentation of this Lambda 9090 values. So what we do in our software, we added the so-called Lambda 9090 report directly in the measurement software. You can search for some criteria: sample thickness range, mean temperature, product type. What product type means, I can explain a little bit later. You can search in a dedicated location, and you can search for different file types. The HFM 436 and 446 are both NETZSCH instruments, and you see also a check mark, which is called Fox. I'm pretty sure some of you know this instrument from your quality control. This is a machine from one of our competitors, and we were asked by our customers to include the measurements from different machines into our reporting system. So what you get is the result for the different measurements. And in the Lambda 9090 overview, you see all the search results and a statistics table, which gives you the minimum, maximum, average, and standard deviation for thickness, mean temperature, thermal conductivity, thermal resistance. It counts the numbers of samples. It determines the K factor. It allows to add an aging supplement, which is based on the DIN 16165 for polyurethane foams. And finally, you get a result of Lambda 9090, which is the base for the declared Lambda value for CE declaration. The report itself gives you a nice ad hoc overview over the actual quality situation in your daily business. And as I said, it's the direct basis for the declared thermal conductivity, which is the Lambda 9090 rounded to the third digit. Okay, question to you all: is thicker insulation better? I would say, of course, thicker insulation is better because thermal conductivity is a material parameter. Thermal resistance is the resistance a material makes again the transport of heat. So the thicker a wall, the better the thermal resistance. And thermal conductivity, of course, is the thickness divided by R. So when we look in typical products, expanded polystyrene, extruded polystyrene, polyurethane, polyiso, with its product standards, and of course there are also more materials that you are going to produce thicker and thicker and thicker. But those are the classical ones that are used on the wall outside. What happens in a heat flow meter? The most used sample size in Europe is 300 times 300 millimeters. And when you look in the DIN 12667, the maximum sample thickness regarding this standard is 50 millimeters for that standard. If you really stick to the standard, of course, you can measure thicker samples in this device, but then you need to adapt calibration and things like that, and you find some workarounds. Okay, but if you stick to the standard, it's 50 millimeters. The question is what to do with a 100 millimeter sample to get reliable results. What a couple of our customers are doing is slicing. If you have a foam material, you easily can slice it from 100 to 425 millimeter samples. Maybe in this case, as a product type XPS 100 millimeter. And it's pretty convenient because you can include all this measurements on that 100 millimeter sample based on a product type filter, and now it comes easily to your Lambda 9090 calculation. So what many of our customers are doing, slice a 100 millimeter product type, enter the product type XPS 100 millimeter to our product type database. You can also enter a nominal thickness and a nominal density range. So you can store all your products that you quality control in your daily business in our database. And when you start a measurement on a sample, which could be a sliced 100 millimeter product, you can dedicate it to the product type 100 millimeter. If you insert the sample and the instrument tells you by entering the weight of the sample that the density is not in that range, the instrument gives you the first alert that you don't have to start the thermal conductivity measurement because it's already out of the density range. This is a real first indicator that there is somewhere a kind of quality issue. You can add several product types, also reference materials. So you can also do a statistic on reference material based on that product type. And the Lambda 9090 calculation is based on the product type filter. So you every time you have a sample of, let's say, 25 millimeters, but you use it for polyurethane 100 millimeters, polyurethane 250 millimeters, and you do a really product type related Lambda 9090 report at a mouse click. And this is really efficient. But what can I do if I produce glass wool? You cannot slice glass wool that easy, like you see in the picture in the red, in the right corner. Yeah, welcome our newest member of our HFM 446 family, which is the Lambda large version, which has 600 times 600 millimeter sample and a maximum sample thickness of 200 millimeters. Yeah, this is the most used instrument, let's say, in the glass wool industry. Okay, now we are on a point where I want to talk about future visions. I want to give you an outlook of what is my understanding about increasing efficiency in QA, and I want to give you an outlook on our ideas, where we are working on, where we are thinking about, and I would really welcome it if you give me feedback on that ideas and how you could imagine to improve the future in your daily quality control. As I said, we are talking about inserting a sample, pressing a button, and getting a result. Up to now, we only talked about thermal conductivity. But on your side, it's not all about thermal conductivity. It's about behavior in case of fire. It's about mechanical strength of your material. In every QA that I stepped in, I saw a heat flow meter, a universal testing machine, and a fire tester, small fire testers. So those are the values that are the most interested values for manufacturers all over the globe. And all the manufacturers all over the globe are producing in different plants all over the world or all over Europe. And your target everywhere is the same: best product quality, conformity to standards, efficient documentation, and timely communication into production if there is an issue. The documentation includes weight and dimensions. The documentation includes temperature and maybe humidity. Heat flow niveau, is my material good or bad? It includes the temperature gradient. It includes the density, the mechanical strength values, values about humidity absorption, production date and lot number of your product. And from my point of view, when we talk about connected production plans, similar challenges in the production plans, similar challenges in production and quality control, I think in that region it's time now to think in cloud solutions. And what we are working on at the moment and what I show you now, it's just a rough draft of my idea to help you increasing your daily business. And this looks like that. Imagine you have different locations, different users, different instruments. In this picture, I only show heat flow meters, but there are also universal testing machines which are producing values. And the challenge is, and this is where we are working on, to find a common interface file format for all that data. And what I have in my mind, you see here a nice overview, total users in your company 2, instruments registered 4, the total measurement that we carried out over 7,000, documented in transparent tables. You can imagine that there could be a user rights management overview over different plans, overview over different instruments, overview over next calibration, last calibration, customer service visits, calibration stability, user detailed data, communication, and all that stuff. And it finally ends in an adaptable dashboard like you see it here. Everybody in your company who is working with the quality of your product can simply filter based on product types, based on date, last week, last month, yesterday, based on, I don't know, based on the shift that is running at the moment. Every time, everything is possible. What you see here is statistics on average and thermal conductivity, average and density, average and density depending on product type, average duration of measurements, Lambda 9090 statistics, histogram of thermal conductivity, and the average thermal conductivity per month over a year view. And let's say like this, we are working on a system like that, and we want to bring the first users in hopefully a time slot of the next 4 to 6 months into a test environment and really learn from you who are challenged by those daily measurements day by day. So we would really like to have people in our beta test phase with their instruments, with their input, and with their experience to improve planned, really planned network, instrument network, user network, location network throughout your company. This is, of course, not only in my mind for our heat flow meters, which are the newest heat flow meters on the market. We want to include everything what you can imagine. If you like to, we offer thermal conductivity measurement seminars. We're collecting at the moment potential attendees on that. We have no dates safe up to now. At the moment, we have a bunch of people registered, not that much. If we have a certain kind of number of potential attendees, we will fix the date and you will hear from us. So you have the chance to register, to pre-register for our seminars on thermal insulation on that website. And finally, I would say maybe you have some questions where I recommend the different units from our steady state thermal conductivity portfolio. And here is an overview. We have the HFM 446 Lambda small, medium, and large, and the guarded hot plates. In that case, we recommend the guarded hot plates for the region or the areas of certification of insulating materials in construction, and for R&D, as well as for certification in the high temperature field, certification and R&D in the high temperature field. The heat flow meters, when we look at the small heat flow meter, we recommend it for the general quality assurance of insulating materials and the R&D of insulating materials, concrete, plaster, and so on, in all regions where CE compliance plays no role, because CE compliance recommends a 300 times 300 millimeter device, which we have with the Lambda medium, which is of course suitable for all the CE compliant quality assurance stuff. And the Lambda large is mainly the unit which is used for glass wool over 50 millimeters. Yeah, now I'm in the end of my talk, and hopefully I gave you a nice overview over products and technologies, and now I'm open for questions. And I see, let's see if we have something. No, not up to now. Someone raised his hands. Yeah. Okay. Yeah, no problem. We have a question, but this is a question where we should think about, or we should answer later on. Nikolai, I would contact you directly after the webinar if it is okay for you, and yeah, to talk in more detail about your needs and about your dedicated questions. Okay. Okay. So, do we have more questions? No questions up to now? Or is someone still typing? Let's wait for another 2 minutes or something like that. Right at the moment, I recognize that I forget to write down my email address. And my email address is, you see my name here in that slide, which is Alexander Frenzel. My email address is alexander.frenzel@netzsch.com. The best would be, which is of course possible, to contact me via LinkedIn. You will also see from time to time interesting articles about our different instruments, about the applications on that channel. So I'm really active on LinkedIn. So whenever you have an account, yeah, you can contact me there. And of course, on my email address, alexander.frenzel@netzsch.com. Or I have all your contact data from the webinar registration. So I try to contact you also via LinkedIn, proactive. So, and if you have no more questions, I would like to say thank you very much for attending. Tell your colleagues what you think about our webinars. Try to get them in the next time. Give me your feedback, what you think about the webinar, what we can improve, what we should do different. Give me your impression of interesting topics for you. Maybe we could align our program of webinars. And yeah, from my point of view, that's it. And have a nice day. Thank you and welcome back to one of our next webinars. Thank you very much. See you.